Functional series means that a common member of this series is any function. A partial case of such series is power series. It means that common member of such a series looks like this: CO plus C1 multiplied by x plus C2 multiplied by x squared plus and so on. So here SO and so on, not SO but CO and so on Cn are called coefficients of power series. So here we may find partial sum of this power series, which is a function of the variable x. So how to find convergence area of the power series, which looks like this: 1 plus x squared and so on. How to find? This series we may consider as geometric progression, because here the next member we may find multiplying by x. So 1 multiplied by x is equal to x multiplied by x is equal to x squared, and so on. That's why we may consider it as a geometric series. So we know that geometric series converges when this modulus of x is less than 1. It means that x should be between negative unit and positive unit. It means that convergence area of this geometric series is this interval from negative unit to positive unit. Abel's theorem says that if the power series converges when x is equal to xo, which is not equal to 0, then it converges, and at the same time absolutely at all the values of x such that they are less than modulus of xo. If the power series diverges when x is equal to x1, then it diverges at all values of x greater than x1. It follows that there is such a number, a capital R, non-negative, that when modulus x is less than this capital R, series is convergent, and when modulus of x greater than R, series is divergent. Here, if power series converges not only at x is equal to 0, then there exists such positive number R, possibly infinite, that the series absolutely converges in the interval of from negative R to positive R and diverges everywhere outside of this interval. And number R we call a convergence radius, and this interval from negative R to R we call interval of convergence of power series. At the ends of this convergence interval, when x is equal to positive negative R, series may be convergent or divergent. So we may find an expression for the radius using this sum. Here, from D'Alembert criterion or D'Alembert test, we know that series will be convergent if limit when n tends to infinity of next member divided by previous is less than unit. So here we may substitute this expression of powered series instead of un plus 1 and un, and cancel both powers of x, and we see that here we have modulus of x multiplied by such limit should be less than unit. We may carry this limit to the right hand side and see that modulus x should be less than this. It means that this expression gives us formula to find radius of convergence. So, to find such radius, we have to calculate limit when n tends to infinity of Cn divided by Cn plus 1. In this example, let's find convergence area of this power series. We see that C in this case is equal to this expression, standing before powers of x. So to find radius of convergence, we have to calculate such limit when n tends to infinity, Cn divided by Cn plus 1. We see that this limit will be equal to square root of 3 divided by 2. So interval of convergence of this series is equal to this. And we may explore convergence of this series at the ends of this interval. When x is equal to negative square root of 3 divided by 2, we see that here we have sign alternating series, and we may check by Leibniz test its convergence. We see that members are decreasing by absolute value, and common member of this series tends to 0 when n tends to infinity. So series is convergent when x is equal to negative square root of 3 divided by 2. When x2 is equal to positive square root of 3 divided by 2, here we have generalized harmonic series when alpha is equal to 2, so it's also convergent. So we may say that the convergence area of this series is equal to the total segment from negative square root of 3 divided by 2 to positive square root of 3 divided by 2.